Have you ever wondered what it would be like to witness Earth's most powerful storms? Not from the safety of satellite imagery or storm shelters, but from the heart of the chaos itself. I am the Chrononaut. I drift through time, and today I want to share a memory of when our planet showed its true atmospheric power. Close your eyes. Take a breath. We're jumping back to 90 million years ago. We arrive in an instant. The heat hits first. Even floating a mile above the western interior seaway, the air is thick, heavy, almost syrupy with moisture. This is not the Earth you know. The temperature at sea level pushes 110 degrees Fahrenheit. In the shade, at the poles. Here, in what will someday be Kansas, the ocean below simmers at nearly 120 degrees. I need you to understand the world that makes these monster storms possible. The Cretaceous period represents Earth at its most extreme greenhouse state. This isn't just a warm phase. It's a fundamentally different planet. Carbon dioxide levels hover at 1,000 parts per million, nearly 3 times your modern levels. Methane, that potent greenhouse gas, exists at concentrations that would trigger climate emergency protocols in your time. The atmosphere is thick, heavy, laden with water vapor at levels that defy modern comprehension. Let me paint you a picture of this alien Earth. I'm floating above the western interior seaway, a body of water that has no modern equivalent. This isn't just a large sea. It's a continent-splitting ocean that connects the Arctic to the Gulf of Mexico. 2,000 miles long, 1,000 miles wide at its broadest point. It divides North America into 2 separate landmasses, Laramida to the west, Appalachia to the east. But it's not the size that makes this sea special. It's the temperature. Fed by equatorial currents that flow unimpeded from the Tethys Ocean, blocked from any cooling polar influence, the western interior seaway has become a massive solar collector. The surface water maintains temperatures between 115 and 125 degrees Fahrenheit year-round, not in isolated hotspots, but across millions of square miles. To understand how alien this is, consider that modern tropical oceans rarely exceed 85 degrees at the surface. The hottest recorded sea surface temperature in your era was 95 degrees in a small area of the Persian Gulf. The entire western interior seaway exceeds that by 20 to 30 degrees. It's not just warm, it's a different state of matter, a different interaction between ocean and atmosphere. The water itself behaves differently at these temperatures. Its density is lower, its capacity to hold dissolved gases reduced, its evaporation rate exponentially higher. Swimming in it would feel like moving through hot soup rather than water. The boundary between liquid and vapor blurs in the intense heat. Steam fog rises constantly from the surface, creating a permanent haze that extends hundreds of feet into the air. Above this maritime furnace, the atmosphere has been transformed. The air pressure is about 20% higher than in your era, not from any fundamental change in gravity or atmospheric mass, but from the thermal expansion of gases. The entire atmosphere has swollen in the heat, creating a thicker blanket around the planet. But it's the humidity that truly sets this world apart. The air doesn't just feel humid, it is literally supersaturated with water vapor. In your world, relative humidity above 100% causes immediate condensation. Here, the extreme temperatures allow the air to hold water in quantities that violate your understanding of physics. The atmosphere contains more water than air in some regions. Life has adapted to this steam bath world in remarkable ways. I observed pteranodons, those magnificent flying reptiles, soaring on thermals that rise like solid pillars from the superheated sea. Their wings, membranous and flexible, have evolved to function in air so thick with moisture it's almost a different medium. They don't so much fly as swim through the aerial soup. Below them, the sea teems with life adapted to the extreme temperatures. Mosasaurs, marine lizards that have returned to the sea, cruise the surface waters. These aren't the sleek predators of cooler oceans. These mosasaurs have evolved in large surface areas for cooling, behavioral adaptations for thermoregulation, metabolisms that function at temperatures that would cook modern reptiles. Schools of primitive fish move in the depths, where temperatures are merely tropical rather than hellish. But even they must surface to feed, entering water hot enough to brew tea. They've evolved proteins that don't denature at these temperatures, blood chemistry that functions in extremis, behaviors that minimize exposure to the hottest surface layers. On the shores of this alien sea, forests grow with tropical exuberance at latitudes that will one day know polar winters. These aren't modern forests. Flowering plants have only recently evolved, and they share the landscape with conifers, cycads, and tree ferns. But it's their growth rate that astounds. In this hothouse world, with unlimited water and extreme temperatures, plants grow at rates that compress decades into years. A forest cleared by storms or dinosaur herds regrows in 5 years rather than 50. Trees reach maturity in decades rather than centuries. The entire ecosystem operates on fast forward, driven by the excess energy available in this greenhouse world. It's a preview of how life responds to extreme conditions, not by retreating, but by accelerating. This is the stage upon which our drama will unfold. A world already pushed to extremes, where the normal rules have been rewritten by heat. Into this setting comes a weather phenomenon that pushes even these extremes to their breaking point. I sense the Hypercane's conception 3 days before it truly begins. In the upper atmosphere, subtle changes cascade through the system. The jet stream, weaker and more meandering than in your cooler world, develops a wave pattern. A trough deepens, creating rotation in the middle atmosphere. Below it, the sea surface waits like gunpowder awaiting a spark. The trigger is laughably small. A minor disturbance in the trade winds, the kind that happens dozens of times each season. In your world, it might spawn a tropical wave that dissipates in days. Here, it's about to initiate a chain reaction that will birth a monster. Day 1. Conception. The rotation begins at altitude and works its way down. This is different from modern cyclogenesis. The extreme vertical temperature gradient, surface temperatures of 120 degrees, upper atmospheric temperatures of -100, creates instability unlike anything in your era. The atmosphere doesn't just want to overturn, it wants to explode upward. By noon of the first day, a broad area of low pressure has formed. Winds at the surface are barely 15 miles per hour, hardly noticeable. But already, the vertical development is extraordinary. Convective towers, individual thunderstorms within the larger system, punch upward past 60,000 feet. In your era, 40,000 feet is exceptional. Here is just the beginning. I position myself to observe the energy dynamics at play. The mathematics are staggering but essential to understand. Water evaporating from the hot sea surface carries latent heat, 2,260 kilojoules per kilogram. In normal conditions, this energy is released gradually as the vapor rises and condenses. But these aren't normal conditions. The extreme temperature difference means water vapor rises faster, reaches colder air sooner, condenses more violently. The energy release is concentrated rather than distributed. Each kilogram of water vapor that condenses releases its energy in seconds rather than minutes. Multiply this by millions of tons of water, and you have a heat engine of unprecedented efficiency. By evening of the first day, the system has organized into a recognizable cyclone. The rotation, driven by Coriolis forces and fed by converging trade winds, has created a spiral pattern 200 miles across. But it's the pressure drop that signals something extraordinary is beginning. In 12 hours, the central pressure has fallen 40 millibars, a drop that would take a modern hurricane days to achieve. Marine life beneath the developing storm senses the change. I watch schools of fish dive deep, seeking cooler waters and stability. Mosasaurs that normally hunt near the surface disappear into the twilight zones. Even microscopic plankton alter their vertical migration patterns. The entire ecosystem recognizes the approaching catastrophe and prepares. Day 2. Transformation. Dawn breaks on a system that has transformed overnight. The broad, disorganized low has contracted into a tight circulation only 100 miles across. This contraction, driven by conservation of angular momentum, has accelerated the winds dramatically. What were gentle breezes yesterday are now gale-force winds today. But it's the eye formation that marks this as different from any modern storm. In your hurricanes, the eye forms gradually through complex dynamics of subsidence and warming. Here, the process is more violent and direct. The rotation becomes so intense that centrifugal force literally flings air outward from the center, creating a partial vacuum. I descend to observe the ocean's response to this atmospheric void. The sea surface, normally held down by 14 pounds per square inch of atmospheric pressure, suddenly experiences only 10. The water responds by rising, not in waves, but as a solid dome. By midday, the sea surface in the eye has risen 100 feet above the surrounding ocean. This isn't the storm surge you know from modern hurricanes. Storm surge is water pushed by wind and pressure differences. This is different. The ocean is being actively sucked upward by the vacuum above. The dome of water is held in place by nothing but the absence of air pressing down on it. The biological consequences are immediate. The rising water brings deep-dwelling creatures to the surface. I observe an encounter between species that normally exist in different depth zones. A deep-water squid, pulled upward by the currents, finds itself in the same water layer as surface-hunting mosasaurs. The normal stratification of the ecosystem has been scrambled. Around the eye, where the pressure gradient is steepest, the sea surface tilts at impossible angles. Water flows uphill, defying gravity to maintain pressure equilibrium. Waves don't break in normal patterns but collide from multiple directions, creating chaotic interference patterns that turn the sea surface into a three-dimensional maze of water. By late afternoon of the second day, wind speeds have reached 150 miles per hour. The storm has achieved major hurricane status. But this is just the adolescent phase of what's developing. The real transformation is happening in the vertical dimension. The storm clouds now tower to 70,000 feet, piercing not just the troposphere but punching deep into the stratosphere. At these altitudes, the storm encounters a different atmospheric regime. The stratosphere is stable, stratified, resistant to vertical motion. But the Hypercanes' updrafts are so powerful they overwhelm this stability, creating a chimney that connects the surface directly to the upper atmosphere. This stratospheric connection has profound consequences. Water vapor, that would normally be trapped in the lower atmosphere is injected directly into the stratosphere. There, it freezes instantly into ice crystals, releasing even more latent heat. But unlike in the troposphere, this heat can't be radiated away efficiently. It accumulates, warming the stratosphere and creating a feedback loop that draws even more air upward. The storm has hacked the planet's atmospheric circulation. It's created a short circuit between surface and stratosphere that bypasses all the normal regulatory mechanisms. The result is a runaway process limited only by the laws of fluid dynamics themselves. Day 3. Monster birth. I position myself at dawn of the third day to witness something that defies belief. Overnight, the storm has undergone a metamorphosis so complete, it seems like a different entity. The eye has contracted from 20 miles across to just 5. Wind speeds have exceeded 200 miles per hour and continue accelerating. But it's the appearance that truly marks this as something beyond normal experience. The friction of air molecules moving at such speeds generates heat. Significant heat. The eye wall has begun to glow. At first, it's just a dim red, like coals in a dying fire. But as wind speeds increase, so does the temperature. By the time winds reach 250 miles per hour, the air itself is incandescent. I need to explain the physics of this phenomenon because it's crucial to understanding what makes a hypercane different from any storm in your experience. When air moves at extreme speeds, friction between molecules converts kinetic energy to thermal energy. At 200 miles per hour, this heating is measurable but minor. At 300 miles per hour, it becomes significant. At 400 miles per hour, the air temperature rises by dozens of degrees from friction alone. But there's a cascade effect. Hotter air can hold more water vapor. More water vapor means more latent heat release when it condenses. More heat release drives stronger updrafts. Stronger updrafts create faster winds. Faster winds create more friction. It's a positive feedback loop with no natural break. By midday of the third day, the hypercane has achieved its mature form. The eye has contracted to a mere 2 miles across, impossibly small for a storm hundreds of miles in diameter. The eye wall towers from sea surface to 80,000 feet, a vertical wall of cloud that glows cherry red from internal heat. Wind speeds have passed 300 miles per hour and show no signs of stabilizing. I position myself within the eye to experience this unprecedented phenomenon. The transition through the eye wall is like passing through a portal between worlds. Outside is ultimate chaos, winds that would atomize any solid matter, temperatures that fluctuate wildly, pressure changes that would crush then explode any closed container. Inside is profound calm, but a calm pregnant with latent violence. The eye is a perfect cylinder, its walls rising absolutely vertical. Looking up from sea level is like peering up from the bottom of a well. If that well were 2 miles wide and 15 miles deep, with walls of glowing cloud. The perspective induces vertigo even in one who has witnessed the formation of galaxies. The sea surface within the eye defies description. The water has risen 300 feet above the surrounding ocean level, forming a mountain of liquid held in place by atmospheric pressure alone. But it's not still. The entire mass rotates slowly, a whirlpool the size of a city. The surface is mirror smooth in the dead air, reflecting the glowing walls in a display that seems to violate the boundaries between elements. But the eye is not empty of life. Here I discover one of evolution's most remarkable adaptations, Quetzalcoatlus northropi, those impossible pterosaurs with 40-foot wingspans. have learned to use the Hypercane as a transportation system. A group of them circles at the eye's edge, timing their entry with instinctive precision. I watch as the lead individual, a mature male with a crest like a Viking sail, makes his approach. He's been tracking the storm for days, using senses we can only theorize about. Perhaps the hollow bones that make flight possible also serve as barometric pressure sensors. Perhaps the electromagnetic disturbances created by the storm register in organs we haven't discovered. Whatever the mechanism, he knows exactly where and when to enter. The pterosaur furls his wings to about half their full span and arrows into the eye through a momentary weakness in the eye wall. The turbulence at the boundary would shred any rigid aircraft, but his flexible wing membranes and pneumatic bones absorb and distribute the stress. In seconds, he's through and into the calm of the eye. What happens next seems to violate physics. The pterosaur spreads his wings fully and is immediately caught by the updraft. But this is no gentle thermal. The air in the eye is rising at over 200 miles per hour, faster than the pterosaur's maximum level flight speed. He's not flying. He's being fired upward like a biological rocket. I follow his ascent, marveling at the adaptations that make this possible. His respiratory system, already incredibly efficient, has evolved to function in rapidly changing pressures. His wing membranes have a cellular structure that remains flexible at temperatures that would brittleize normal biological materials. His eyes are protected by special nictitating membranes that prevent freezing while maintaining vision. 10,000 feet, 20,000, 30,000. At 40,000 feet, ice begins forming on his wings, but the constant motion and heat generated by air friction prevents dangerous accumulation. The temperature has plunged to -60 Fahrenheit, but the pterosaur's countercurrent heat exchange system maintains his core temperature. At 50,000 feet, the pterosaur faces a critical decision. He must find the exact altitude where the rising air in the eye transitions to horizontal flow in the storm's upper circulation. Too low, and he'll be carried higher into conditions even he can't survive. Too high, and he'll miss the optimal wind speeds for long-distance travel. With subtle adjustments of his wing angle and tail position, he samples different altitudes, like a wine connoisseur testing vintages. At 55,000 feet, he finds what he's seeking. The outflow jet, where air accelerates horizontally at 500 miles per hour. With a banking turn that would make a fighter pilot envious, he transitions from vertical to horizontal flight. Now begins one of nature's most remarkable journeys. The pterosaur is traveling at 500 miles per hour, faster than any biological flyer in your era, faster than your early aircraft, approaching the speed of your modern jets. But he's expending almost no energy. His wings are locked in a configuration perfected by millions of years of evolution, creating maximum lift with minimum drag in these specific conditions. I track his trajectory as he rides the storm's upper circulation. In 1 hour, he covers 500 miles. But he's not simply being blown randomly. By subtle adjustments of altitude, he can choose different wind speeds and directions. The storm circulation is like a three-dimensional highway system, with lanes at different levels leading to different destinations. This pterosaur is migrating from feeding grounds in what will become Montana to breeding grounds in future Mexico. A journey of 2,000 miles that would normally take weeks of exhausting flight. Using the Hypercane, he'll complete it in 4 hours while expending less energy than a short hunting sortie. But he's not alone in exploiting this atmospheric elevator. I observe dozens of pterosaurs at various altitudes. each riding different parts of the storm's circulation. They've turned a catastrophic weather event into a transportation network. Some are migrating, others are dispersing to new territories. A few seem to be riding the storm just for the efficiency of it, banking biological energy for future needs. Let me pull back from individual stories to show you the storm's broader impacts, because a hypercane is not just a local phenomenon. By the fourth day, the storm has grown to influence weather patterns across half the continent. Its outflow creates a dome of high pressure that diverts the jet stream around it. Weather systems that would normally track straight west to east are forced into meandering patterns that bring unusual conditions to regions thousands of miles away. In what will become the Rocky Mountains, the disrupted flow causes unprecedented rainfall on eastern slopes, while western slopes experience intense drought. Rivers swell beyond their banks, carving new channels that will persist as valleys in your time. Meanwhile, areas that normally receive reliable rainfall are parched, their ecosystems stressed by unexpected drought. The hypercane is redistributing more than just water. The violent mixing of ocean layers brings minerals from the deep to the surface. Iron, phosphorus, and other nutrients that normally remain locked in deep waters are suddenly available to photosynthetic organisms. In the storm's wake, the sea blooms with unprecedented intensity. I witness a phytoplankton bloom that turns the ocean green for hundreds of miles. These microscopic plants, suddenly given access to nutrients that have been locked away for millennia, reproduce with explosive speed. The bloom is visible from space, if any eyes existed to see it, as a green spiral marking the storm's passage. This biological explosion cascades up the food chain. Zooplankton that feed on phytoplankton experience population booms. Small fish that eat zooplankton suddenly find unlimited food. Larger predators converge on the area. Within days of the storm's passage, the barren blue waters become a biological hotspot that will persist for months. But the storm's influence extends beyond the ocean. On land, the hypercane's approach triggers behaviors honed by millions of years of evolution. Dinosaur herds that normally maintain territories begin migrations to sheltered areas. Not panicked flights, but organized movements along routes carved by countless generations. I follow a herd of hadrosaurs, duck-billed dinosaurs the size of elephants. They've sensed the storm's approach through mechanisms that remain mysterious. Perhaps they feel the infrasonic vibrations through their feet. Perhaps they detect the electromagnetic anomalies through magnetite crystals in their skulls. Perhaps they simply recognize the pattern of pressure changes that precede these storms. The herd moves with purpose, adults protecting juveniles, strong individuals helping weak. They're heading for a canyon system 50 miles inland, far enough from the coast to avoid storm surge, oriented to deflect the worst winds, with caves large enough to shelter the entire herd. This knowledge isn't learned but inherited, encoded in genes by natural selection. Herds that sheltered properly survived. Those that didn't left no descendants. As the hypercane makes landfall, I position myself to witness destruction on a scale that redefines the concept. The storm surge isn't the 10 or 20 feet of your worst hurricanes. The dome of water beneath the eye, held up by atmospheric pressure differential, is 300 feet high. When this mountain of water encounters the continental shelf, it doesn't gradually rise. It maintains its height until the seafloor beneath it shoals. The result is a wall of water 300 feet high moving at 70 miles per hour. The forward speed of the storm. It doesn't break like a wave. It's a vertical cliff of ocean advancing across the landscape, maintaining its height through the constant suction of the eye above. Everything in its path isn't just flooded, it's erased, I watch a coastal forest of primitive conifers encounter this liquid wall. The trees, some standing for centuries, disappear in seconds. Not knocked down, not broken. Simply gone, incorporated into the moving mass of water and debris. The storm surge has become a horizontal waterfall, carrying millions of tons of sediment, vegetation, and any life too slow to escape. But it's the wind that truly demonstrates the Hypercane's power. At 400 miles per hour sustained, with gusts exceeding 500, air behaves more like a fluid than a gas. The dynamic pressure, the force exerted by moving air, exceeds 3,000 pounds per square foot. To put this in perspective, your strongest building codes, designed for winds up to 200 miles per hour, generating pressures of about 100 pounds per square foot. Nothing can withstand this force. I watch the wind encounter a ridge of solid granite, rock that has stood since the Permian. The wind doesn't flow over or around it. Instead, the incredible pressure differential between windward and leeward sides causes the rock to spool. Sheets of granite peel off like layers of an onion, launched as projectiles that embed themselves in hillsides miles away. The sound is beyond description. It's not just volume, but frequency. The Hypercane generates acoustic energy across the entire spectrum, from infrasound that propagates through the Earth's crust to ultrasound that causes materials to resonate and shatter. It's a roar that bypasses the ears and registers directly in the bones, a planet-scale scream of tortured air. In the midst of this chaos, I observe moments of bizarre beauty. The friction-heated air in the eye wall doesn't just glow. It creates its own lightning in continuous sheets. This isn't the intermittent lightning of normal storms, but a constant electrical discharge that turns the eye wall into a cylinder of plasma. The electromagnetic pulse from this discharge creates localized auroras, sheets of green and purple light that dance across the sky in broad daylight. Where the superheated eye wall air meets cooler surrounding air, the temperature differential creates optical effects that seem to belong more to fantasy than physics. Mirages stack vertically, creating the illusion of cities floating in the sky. Light bends in ways that make the horizon appear to curve upward. The storm has become its own planet with its own optical laws. The biological toll of landfall is catastrophic, yet selective. Animals that took proper shelter survive. A family of small mammals, early primates no larger than squirrels, huddle in a deep burrow as the storm passes overhead. The adults have packed the entrance with mud and vegetation, creating an air pocket that maintains pressure as the eye passes over. They'll emerge to a transformed world, but alive. In contrast, a group of pterosaurs that failed to evacuate in time faces the full fury of the storm. I watch them attempt to take flight as the eye wall approaches. For a moment, it seems they might escape. Their powerful wings beat against the wind, gaining altitude. Then the wall of air hits them. The pterosaurs don't just fail to fly, they disintegrate. The pressure differential across their wing membranes causes them to rupture explosively. Their hollow bones, evolved for lightness, implode then explode as pressure waves pass through them. In seconds, creatures that ruled the skies are reduced to organic debris scattered across miles of landscape. Yet even in this destruction, life finds opportunities. Those pterosaurs riding the storm's upper circulation are dispersing to new territories. Seeds and spores caught in the updrafts are being transported across genetic barriers, introducing new possibilities to isolated ecosystems. The storm is destroying, but also creating, ending some evolutionary lines, while opening new paths for others. As the Hypercane moves inland, it begins to weaken, but slowly, reluctantly. Unlike your hurricanes that dissipate rapidly over land, the hypercane has such massive angular momentum that it maintains organization even as its energy source is cut off. It's like a massive flywheel continuing to spin from sheer inertia. The rain it produces defies comprehension. Not the inches of your hurricanes, but feet per hour. The water doesn't fall as drops, but as solid sheets, turning the air opaque. Rivers form instantly on hillsides, converging into temporary waterfalls that cascade off cliffs. Valleys become lakes in minutes. The landscape is being reformed by water moving at geological speeds. But perhaps most remarkable is what happens in the upper atmosphere. The hypercane has injected millions of tons of water vapor into the stratosphere, where it doesn't belong. This water freezes into ice crystals that will persist for years, creating a high-altitude haze that affects global climate. The storm's influence will outlive it by decades. Similarly, the massive mixing of ocean layers has altered currents that will take centuries to restabilize. Cold, nutrient-rich bottom water now sits at the surface. Warm surface water has been driven to depths where it doesn't belong. The ocean's entire circulation pattern has been scrambled, with effects that will ripple through marine ecosystems for generations. As the storm finally begins to dissipate on its fifth day, I position myself to observe its death. A hypercane doesn't simply weaken and disappear. It's too organized, too powerful for such a mundane end. Instead, it fragments catastrophically. The eye, which has maintained its integrity for days, suddenly becomes unstable. Resonances in the flow create wobbles that amplify rapidly. The perfect circular eye distorts into an ellipse, then a figure 8, then chaos. The single massive vortex breaks into multiple smaller vortices, each still hurricane strength, spiraling outward like shrapnel from an atmospheric bomb. These daughter storms will persist for weeks, carrying the hypercane's energy far from tropical waters. They'll bring moisture to continental interiors that rarely see rain. They'll trigger secondary weather systems through their interactions with normal atmospheric patterns. The hypercane is dead, but its offspring ensure its influence continues. In the storm's wake, I survey a transformed world. The landscape has been scraped clean for hundreds of miles inland. Not just vegetation removed, but topsoil stripped away. Bedrock exposed, new drainage patterns carved. Sediments that took millions of years to accumulate have been redistributed in days. Future geologists will puzzle over the massive discontinuity in the rock record. But life is already returning. Plants adapted to catastrophic disturbance are the first to appear. Their seeds, evolved to survive passage through the storm, germinate in the nutrient-rich debris. Within days, green shoots appear. Within weeks, the bare ground is covered with fast-growing pioneers. The forest will return, different in composition, but recognizable in function. Animal survivors emerge from their refuges to find their world rearranged. Territories no longer exist. Landmarks have vanished, but they adapt with remarkable speed. New hierarchies form. New territories are established. The fundamental drive to survive and reproduce reasserts itself. Life flows into the vacuum created by destruction, like water finding its level. The evolutionary implications of hypercanes extend far beyond immediate survival. These storms create what biologists call genetic bottlenecks, events where populations are severely reduced, concentrating genetic variation. But they also create genetic highways, dispersing organisms across barriers, introducing new genetic material to isolated populations. I observe a small population of theropod dinosaurs that survived the storm in a protected valley. They're now cut off from others of their species by new water barriers created by the storm. In isolation, they'll evolve in unique directions. Perhaps they'll develop new hunting strategies, new social structures, new physical adaptations. The storm has created an evolutionary experiment that will play out over millions of years. Similarly, plants whose seeds were carried to new environments by the storm-faced novel selective pressures. A fern adapted to shaded forest floors finds itself in open grassland. Most will die, but a few with slightly different genetic profiles will survive. Over generations, they'll evolve into something new, perhaps the ancestor of a whole new plant family. The storm has shuffled the evolutionary deck and dealt new hands. The Hypercane has also created new ecological niches. Where the storm's surge deposited marine sediments far inland, salt-adapted plants can colonize. Where intense scouring exposed mineral-rich rock, specialized organisms that can process these nutrients gain advantage. The uniform pre-storm ecosystem has been shattered into a mosaic of microenvironments, each supporting different communities. As I prepare to leave this chronicle of destruction and renewal, let me share the global perspective. The Hypercane I've shown you is not unique. In the Cretaceous greenhouse, 3 to 5 such storms develop each year. They're not anomalies, but integral components of the climate system. The biosphere hasn't just adapted to them. It's evolved to depend on them. The massive ocean mixing maintains nutrient cycles that would otherwise stagnate. The extreme rainfall events fill inland lakes that would otherwise dry up. The atmospheric injection of water vapor helps maintain the greenhouse conditions that keep the planet warm. Remove Hypercanes from the Cretaceous, and the entire system would collapse into a different equilibrium. This is perhaps the most profound lesson of the Hypercane. What seems like pure destruction from one perspective is revealed as necessary renovation from another. The storm is not separate from the ecosystem, but part of it. Destruction and creation are not opposites, but complementary faces of the same process. The Hypercane is Earth's way of preventing stagnation, of ensuring that energy and nutrients keep circulating, of maintaining the dynamic disequilibrium that defines living systems. Your modern world exists in a brief calm between such extremes. Ocean temperatures cool enough to limit hurricane intensity. Atmospheric conditions stable enough to prevent Hypercane formation. But the physics that created these monsters hasn't changed. The equations wait patiently in the mathematics of fluid dynamics, needing only sufficient heat to reawaken. Climate models suggest ocean temperatures would need to rise by 15 to 20 degrees Celsius globally to permit Hypercane formation. That seems safely impossible until you remember that local conditions can vary dramatically from global averages. A volcanic eruption beneath shallow seas, an asteroid impact in tropical waters, even extreme greenhouse gas concentrations could create temporary conditions suitable for these storms. More concerning is the possibility of almost Hypercanes, storms that approach but don't quite reach the threshold for self-sustaining friction heating. A hurricane with sustained winds of 300 miles per hour would be far short of a true Hypercane, but would still exceed anything in human experience. The damage would be unprecedented, the death toll catastrophic, and your coastal civilizations are utterly unprepared for such a possibility. Feel yourself returning now, the heat fading, the winds calming, time accelerating beneath us. We're back in your present, where the oceans are cool enough to limit hurricanes to Category 5, where wind shear prevents storms from reaching the stratosphere, where you've built a civilization assuming the worst possible storm is one with sustained winds of 180 miles per hour. When you watch the weather report tonight, when they speak of major hurricanes with genuine concern, remember that these are gentle breezes compared to the hypercanes. Remember that your entire existence, your coastal cities, your global shipping, your very assumption that weather has limits, depends on the ocean staying cool enough to prevent these monsters from forming. The Hypercane stands as both a monument to Earth's capacity for violence and a humbling reminder of the narrow conditions that permit civilization. Every climate model that shows warming oceans should be viewed not just as abstract numbers, but as steps toward reawakening the physics of Hypercanes. They are not mythology, they are not theoretical. They are mathematical certainties given the right conditions. The fact that those conditions haven't existed for millions of years doesn't mean they can't return. The atmosphere has a memory written in equations, and those equations remember how to build storms that reach for space. In your time of climate change and warming seas, understanding the Hypercanes of the past becomes more than academic curiosity. It becomes a warning written in physics about the thresholds we must not cross, the boundaries we must respect, the sleeping monsters we must not awaken. The next time you feel hurricane-force winds or see storm damage on the news, remember that you're witnessing the weak offspring of Earth's true atmospheric potential. Be grateful for the cosmic accident of timing that placed human civilization in an era of weak storms. And perhaps be a little more cautious about pushing the climate toward conditions that might awaken the Hypercanes from their long sleep. Until we meet again in the streams of time, this has been a memory from the Chrononaut.